Good morning, all of you. My name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we will going to discuss about our vestigial sideband modulation, which is a special type of AM modulation, or you could say it is the part of amplitude modulation systems. So these are the outlines. We're going to start up with the introduction. Then we will going to define about vestigial sideband modulation. What do you mean by vestigial sideband? Then we will going to discuss about the spectrum of vestigial sideband signals. Then how we will going to generate the vestigial sideband signal, which will be followed by the time domain representation of VSB signal. Then we will going to discuss about the coherent detection method of VSB signal. And finally, we're going to conclude by discussing some of the advantages as well as the disadvantages associated with our vestigial sideband signals. So, to produce the SSB signal from the DSB signal, ideal filters should be used. This we had already discussed in our previous lecture while discussing the detection method in our SSB signal. We will be requiring a very sharp cutoff filters in order to separate the two sidebands in order to get the single sideband. So this particular figure is basically showing your DSB-SC waveform as a whole. It is containing both this upper sideband as well as lower sideband. And if we want to specifically select only a single sideband, that is either upper sideband or lower sideband, we will be requiring a very sharp cutoff filters which can easily separate the two sidebands, and we can selectively in a state to get either upper sideband or lower sideband, which is nothing but your single sideband signal. So in vestigial sideband system, one sideband and the vestige, or you could say the portion of the other sideband, are transmitted together. So obviously there has to be certain utility that why do we actually needed to transmit one sideband along with some portion of the second sideband. Although in our SSB systems we had already discussed that both the two sidebands will going to get the same information signal. If anyhow we are in a state to get one of the sideband completely, then our purpose of communication could be fulfilled. But still in this particular case, there are specific sort of signals which possess most of the information content, or you could say significant information content at the lower frequency bands, and in this particular cases it would be very difficult to separate those frequency bands properly, just because we do not have any ideal filters, and due to this reason we cannot have very sharp cutoff frequency filters. So anyhow both these bands, that is your upper sideband and lower sideband, will become quite inseparable, or we could say that if we are trying to separate those sidebands, then we will going to face the loss in our received signals. So the resulting signal has the bandwidth greater than the bandwidth of the modulating signal, or you could say your baseband signal, but it is less than the DSB-SC signal bandwidth. So typically the vestige or the portion of the signal that is transmitted is around 25% of the signal bandwidth. So one complete sideband and another sideband's 1/4 of the signal bandwidth we are basically transmitting as a vestige or the portion of the another sideband. So vestigial sideband modulation is a modulation technique which will allows us to the transmission of one sideband in addition with the part or vestige of the other. This is what we have discussed so far about the vestigial sideband modulation. So it is basically a compromise between the DSB-SC and SSB-SC modulation, since we are transmitting one complete sideband and some portion of another sideband. So obviously the bandwidth requirement of VSB-SC signal is greater than your SSB-SC signal, but it is quite lesser in comparison to your DSB-SC signal. So instead of transmitting only one sideband as SSB, VSB modulation transmits a partially suppressed sideband and a vestige of the other sideband. So this point will same as we have discussed the above one. So this particular figure is basically showing the spectrum of vestigial sideband signal. So if we closely observe that this particular above figure is basically showing the spectrum of our message signal, which is your baseband signal, which contains maximum frequency component of FM. So this is the frequency, or you could say spectrum of your message signal. And this particular figure, lower figure, is basically showing the spectrum of vestigial sideband signal, in which we are basically transmitting the complete upper sideband and some portion of the lower sideband. So in this particular figure, this particular portion is basically showing your USB, and this is the negative frequency part of your upper sideband. So here also we are basically transmitting this complete sideband and some portion of the lower sideband. So that portion or the range of frequencies, we are calling them just as representing them with this FV, and this complete frequency range or bandwidth, you could say, that is your FM. So the bandwidth requirement of your vestigial sideband signal turns out to be this vestige portion plus this complete FM, that will be equal to FV plus FM. So obviously in case of single sideband suppressed carrier systems, we will be having the bandwidth requirement of FM, whereas in this particular case we will be having the bandwidth requirement of FV plus FM, where FV is the vestige or the portion of the another sideband. This particular figure is basically showing the spectrum of our vestigial sideband system. Similarly, this is basically representing the negative frequency counterpart of this upper sideband. Another variant of vestigial sideband is also possible, where we will going to have the LSB complete and some portion of our USB, and in the similar manner, that negative frequency counterpart will also going to contain your LSB and some portion of your USB. So next, how do we going to generate the vestigial sideband signal? So initially what we have to do is we have to generate a DSB-SC AM signal with the help of product multiplier, where we are going to apply our message signal MT and AC cos of 2 pi FCT, which is nothing but your carrier signal. And when we will going to pass this particular signal through the product multiplier, we will going to get this DSB-SC modulated waveform, which will going to pass through a specific sideband filter, which will going to produce us our vestigial sideband modulated signal. But since in our VSB systems, we have to pass one complete sideband and some portion of other sideband, so obviously we will be requiring a specific sideband shaping filter, whose transfer function would have been given here as your HF. So while passing through a specific filter, we will going to get the vestigial modulated waveform, which will be denoted as your ST. So here the HF will going to contains a specific important role, since without this specific filter HF, we are not in a state to develop the VSB modulated waveform. So in our upcoming slide, our focus will be on understanding the working of this sideband shaping filter. So the important point is the response of that sideband shaping filter. What type of response we are required, and what basically it's look like. So the exact design of the filter depends upon the desired spectrum of the VSB modulated waveform. Obviously, which frequency bands are desired. So we just have to filter out those undesired frequency band, and we have to pass on all the desired frequency band. In desired frequency band, we will going to contain one complete sideband and some portion of the another sideband. So this is our desire. So the vestigial sideband filter requires to have the vestigial symmetry found around FC. So if you closely observe that, this particular figure is showing the typical transfer function of the sideband filter. So this is just for example purpose, you could consider this is a typical transfer function characteristics, but important point is it is symmetrical around FC. That is this symmetry I am talking about. This is symmetrical to this particular portion. So obviously exact transfer function of the filter we are not talking about, but still any typical filter which will going to serve the purpose to produce this VSB waveform, this must have to have this sort of symmetry around FC. So when we will going to discuss the mathematical details of that filter, then you came to know that what symmetry we are talking about. So this is the typical transfer function of the sideband filter. So now we're going to discuss the time domain representation of VSB signal. How does it look like? So since VSB signal is also a band pass signal, and any band pass signal can be represented in this particular format, that is in phase component multiplied with your cosine term and quadrature component multiplied with your sine of 2 pi fct. So any band pass signal can be represented with this form. So since VSB signal is also a band pass signal, so this could also be represented in the same form. So here SI of t is the in phase component and SQ of t is the quadrature component of the ST. So the in phase component may be derived from ST by first multiplying ST by cos of 2 pi fct and then passing the product through the low pass filter. So obviously if we have to evaluate this SI of t, what we have to do is we just simply have to multiply this ST with cos of 2 pi fct and simply pass it through the low pass filter. In the similar manner, if we have to find out this SQ of t or quadrature component of that particular signal, then we just have to multiply our signal ST with sine 2 pi fct and again we have to pass it out through a low pass filter. So this is how we will going to obtain this in phase component as well as the quadrature component. In the frequency domain, the in phase component can be written as S of f minus fc plus S of f plus fc, where f is lying between minus w to plus w. Obviously this is talking about our bandwidth range. The maximum frequency component or the bandwidth range in which that particular filter is working is your minus w to plus w. So if you closely observe that in phase component is nothing but it is the multiplication of ST with the cos of 2 pi fct. So if we suppose that the Fourier transform of ST would have been given as your S of f, then when we will going to multiply that signal with cos of 2 pi fct, then Fourier transform we will going to have is your S of f minus ft plus S of f plus fc. So that will get shifted with the carrier frequency fc, and the in phase component value will be 0 elsewhere, that is beyond that value of w, its value will be equal to 0. So in the similar manner we could also find out the quadrature component. So SQ of f or the Fourier transform version of your SQ of t, that will be equal to j times of S of f minus fc minus S of f plus fc. Again here also S of f is nothing but the Fourier transform of your S of t, and since we have multiplied that particular signal with sine of 2 pi fct, so that particular spectrum will get shifted towards the frequency of your fc. So here also the value of SQ of f will be this in these frequency range and its value will be equal to 0 elsewhere. So now the spectrum of the vestigial sideband signal is S of f is equal to half of AC m of f minus fc plus m of f plus fc times of h of f. If you closely observe about this particular figure, here we will be having our message signal mt and AC cos of 2 pi fct, which is nothing but your carrier signal. Both these signals will get multiplied and we are getting this DSB SC waveform, and that particular signal will get passed through the sideband shaping filter. So now the spectrum of the vestigial sideband signal can be given as S of f will be nothing but the product of your message signal with the carrier, and that DSB SC signal will get multiplied with the sideband shaping filter whose transfer function is your h of f. So if you closely observe that I am talking about this is nothing but the Fourier transform of your DSB SC signal. So it will get multiplied with this transfer function h of f, and the product of these two will going to give us the spectrum of our VSB signal. So now SI of f will be equal to half of AC times of m of f minus 2fc plus m of f multiplied with h of f minus fc plus half of AC times of m of f plus m of f plus 2fc times of h of f plus fc. So we have just put this value si of f, that will be equal to s of f minus fc plus s of f plus fc. It will get multiplied with this cos of 2 pi fct. So obviously, in order to find out the in phase component, or you could say that the Fourier transform of in phase component si of f, we just simply have to multiply your sf with cos of 2 pi fct. So we are getting this valuation, that is half of AC m of f minus 2fc plus m of f. Since cos of 2 pi fct could have also been written as e to the power minus j 2 pi fc plus e to the power minus j 2 pi fc by 2. So via applying that particular thing, and after multiplication with that exponential part, we will going to get these four terms. Just check it out, this one and this one. So obviously h of f minus fc, this is for the positive frequency of your phasor, and this is analogous to the negative frequency of your phasor, or you could say exponential term. So we are getting these four terms. Then we will going to pass it out through your low pass filter. So if we are passing that particular si of f with a low pass filter, so obviously the high frequency component which are centered around this your 2fc and this 2fc, they will going to be lost. So we are getting this si of f will be equal to half of AC times of m of f, h of f minus fc plus h of f plus fc. So similar thing we have to perform in order to get the value of SQ of f, or you could say the Fourier transform of SQ of t. So at the receiving side, we basically have to evaluate or get our message signal back. So this is the in phase component, and how we are in a state to get our message signal back when we will going to receive this in phase component at the receiving side. If we closely observe that, if it is having the component of half of AC times of MF is nothing but your message signal, times with h of f minus fc plus h of f plus fc. So by any mean, if this particular term turns out to be a constant value, then that will going to serve our purpose. So let us say the value of h of f minus fc plus h of f plus fc will be equal to unity. This is just a typical assumption. It could be any constant term, just because we are only concerned about this mf. While demodulating, we are in a state to get our message signal or original message signal back. So in that particular case, when h of f minus fc plus h of f plus fc turns out to be unity, our si of f turns out to be half of AC times of m of f. So when we will going to get its time domain version, then we will going to get the in phase component si of t will be equal to half of AC times of mt. So in the similar manner, all this process we will going to apply for quadrature component also. Then what we will going to get is SQ of f will be equal to j times of half of AC times of m of f minus 2fc plus mf times of h of f minus fc minus times of half of AC m of f plus m of f plus 2fc times of h of f plus fc. So again, what we basically do is, in order to get this SQ of f, we just simply multiplied s of f with the sine of 2 pi fct, and we are getting this particular term. So this is again going to have these four terms, and when we're going to pass that particular thing through the low pass filter, so we are only left with this two terms, that is your half of AC times of mf multiplication with this one, and then again half of AC times of mf multiplication with this particular term when we are going to pass through the low pass filter. So now passing through the low pass filter, we are going to have this j times of half of AC times of m of f, h of f minus fc minus h of f plus fc. So SQ of f turns out to be this one, that is half of AC times of m of f, j times of h of f minus fc minus h of f plus fc. So this is your Fourier transform of your SQ of t. So let us say SQ of t turns out to be half of AC times of m prime of t. So basically, inverse Fourier transform of SQF will be equal to SQ of t, and let us say it will be equal to half of AC m prime of t. So this complete inverse Fourier transform, we are writing it as your half of AC times of m prime of t. So thus the VSB modulated waveform in the time domain signal is ST is equal to half of AC times of mt cos of 2 pi FCT plus half of AC times of m prime of t sine of 2 pi FCT. So this will be your ST signal. Let us say this is your equation number 1. So obviously we have evaluated this in phase component and the quadrature component via the previous analysis that we have discussed. So now how are we going to perform the demodulation of VSB-SC signal? So again ST signal is same that we have evaluated in the previous slide. That signal, obviously we are talking about coherent detection technique. So we will going to use the same carrier frequency as we have used at the transmitting side. So that carrier frequency cos of 2 pi FCT, that will get multiplied with this ST, and we are getting this SC of t, and then this SC of t signal, it will going to pass through the ideal low pass filter, which by which we are going to obtain this SO of t, that is output signal, which is nothing but your MT signal. So we have calculated the spectrum of VSB-SC signal as S of f is equal to half of times of m of f minus fc plus m of f plus fc with multiplied with your h of f. This is nothing but the spectrum of our VSB-SC signal. So obviously the Fourier transform of your ST will be equal to your S of f. So this is your input signal to your product multiplier, or you could say your demodulators, coherent detector circuitry. Let us say this is your equation 2. So here m of f is the Fourier transform of the baseband signal, or you could say your message signal. This is quite obvious, we had already discussed it out. Then this signal will get multiplied with this again carrier signal, that is your cos of 2 pi FCT, and then it will get passed through the low pass filter. So the output of the product modulator will be equal to SCT will be equal to ST times of cos of 2 pi FCT. So now taking the Fourier transform of both sides, so ST, the Fourier transform of ST we had already evaluated, that is your S of f, and when it will going to get multiplied with your cos of 2 pi FCT, then frequency translation again will going to take place. So SC of f turns out to be half of S times of f minus fc plus S of f plus fc. So keeping in mind, we are assuming that the Fourier transform of ST will be equal to S of f, and since we are multiplying with cos of 2 pi FCT, so again we will going to get the frequency shifted, or this signal ST will get shifted in the roundabout or in the vicinity of your carrier frequency FC. So we are basically getting this SC of f will be equal to this one. So now putting the value of S of f from equation 2, what we will going to have is SC of f will be equal to 1 by 4 times of, since half is already here, and in your equation 2 also we are going to have a half, so that will get multiplied, and we are going to have this 1 by 4 times of m of f minus 2 fc plus m of f. Then it will get multiplied with the filter, that is filter transfer function, that will be equal to h of f minus fc plus 1 by 4 mf times of mf plus m of f plus 2 fc multiplied with your h of f plus fc. So this shifting in the transfer function of our filter is also coming due to the multiplication with the carrier signal, that is your cos of 2 pi fc. SC of f will be equal to 1 by 4 times of m of f, h of f minus fc plus h of f plus fc, plus 1 by 4 m of f minus 2 fc, h of f minus fc plus m of f plus 2 fc, h of f plus fc. So here in this particular case, I have write it down all the frequency component and collected it in terms of m of f and m of f minus fc and m of f plus 2 fc. So obviously when we are going to pass through the low pass filter, so this lower portion will get vanished and we are left with this upper portion only. So this SC of f will going to contain the message signal m of f with the transfer function of filter, this one. So now when we are going to pass through the low pass filter, we are going to obtain is the same thing that I am talking about. Let us say this is your equation number 3. So this is the Fourier transform of your SO of t, or you could say output signals Fourier transform. So from this particular thing, we should find out the message signal MT. So obviously for the distortionless reproduction of the original baseband signal at the output of the detector, it is necessary that the transfer function of the filter must satisfy the following condition. So obviously the condition we have talked in the past also, that the value of this h of f minus fc plus h of f plus fc, if anyhow this combination or this transfer function of that filter turns out to be unity or any constant term, then by simply taking the inverse Fourier transform, we are in a state to get the message signal back from this S naught of f. So obviously what condition we are talking about, this particular thing h of f minus fc plus h of f plus fc should be equal to unity. This is the typical case that we have shown in our initial slides, that we are talking about the symmetry at roundabout of carrier frequency fc. So if that symmetry will going to possess, the combination of this particular thing will be equal to a constant term, or you could say unity. So here in this particular case, we have say that if h of f minus fc plus h of f plus fc will be equal to 1. So in that particular case, we will going to get the undistorted message signal back. So if during these frequency bands, if this value will be equal to unity, then we are in a state to observe or to retrieve our message signal back. So this particular figure is showing the magnitude response of the VSB filter, and look, this symmetry I am talking about, roundabout at this particular frequency fc, whatever we are whatever portion we are having at this above portion, it is symmetrical at the roundabout at this particular portion. So if you closely observe that, what I am trying to say is, so let us say typical filter response would be like this one, or you could say sharp cutoff filters transfer function should look like this one. But since we are manipulating that transfer function, since we do not possess such a sharp cutoff filter or ideal filter response, we do not possess, we are basically having practical filters which do not possess the sharp cutoff. So roll off factor obviously is there. So if you closely observe that, I am talking about this particular thing and this particular thing. So basically we are omitting this particular portion and we are passing this particular portion. So due to that symmetry, if you closely observe that, this particular portion and this particular portion are almost same. So you just think it of about the symmetrical aspect, what we are talking about, the transfer function of the filter. So easily you will going to get the idea behind what purpose that symmetry will going to fulfill for us. So the sum of the values of the magnitude response mod of h of f at any two frequencies equally displaced above and below the fc is unity. So above this fc and below this fc, we are talking about this one, this is unity. So now taking the inverse Fourier transform of equation t, we basically going to retrieve out the original message signal back. So S naught of t, that will be equal to 1 by 4 times of mt. So obviously this is the attenuated form of your message signal, but after passing through the proper amplifier, we will going to observe, or we will going to get the actual message signal back. So now we are going to discuss about some of the advantages of vestigial sideband signals. So vestigial sideband is the standard for TV transmission and similar signals. So obviously if talk about specific applications such as your speech signal, we do not possess that much problem for SSB signal transmission, just because if we talk about speech signal, they do not possess much significant amount of information at the lower frequency band. So for speech signal sort of application, SSB modulation works very well. But if we talk about the television signal or fax signal, So in those signals, we will going to have significant amount of information at lower frequency component also. So SSB is not a good choice for having these types of TV, or you could say, or fax types of signals. So here we are basically using the VSB signal. So bandwidth saving can be significant if modulating signal are of large bandwidth, as in TV and wideband data signal. So obviously, if we talk about the bandwidth of the TV signal, it is in the order of megahertz, that is typically around 4 to 5 megahertz. So if we are saving significant amount of bandwidth, so we are in contrast with your DSB-SC signal, so we are almost saving around 3 to 3.5 megahertz of bandwidth, which is a significant amount. So now the disadvantages of the vestigial sideband signal. So its bandwidth requirement is somewhat higher than that of the SSB modulation. We had already discussed that in your SSB modulation, we are only transmitting single sideband, that is either upper sideband or lower sideband. Whereas due to the presence of vestige, we are in our VSB systems, along with the one complete sideband, we are also transmitting or passing the portion or vestige of the second, or you could say other sideband also. So that is why the bandwidth requirement is higher in comparison to your SSB signal. So vestigial sideband modulation leads to the complex demodulation process at the receiving end, since a specific filter would have been required. So all this complexity and mathematical analysis of the filter we had already studied. So it will also going to have this complex demodulation process, obviously in your VSB. So hopefully you will get the insight about the VSB modulation systems. Why do we actually need VSB systems, and the mathematical analysis of the filtered part of your VSB signal. So in case of any doubt, you can ask me in the comment section. I'll try to help you out as soon as possible. So these are the references. Thank you very much for your patient hearing.